Well, thank you, Scott, for inviting me this evening. In the minds of future historians, it may be that the late 20th century will be ranked with that of Copernicus in the 16th century, as a time when we took a great leap in our understanding of our place in the universe. I want to tell you about one of the men who pioneered this field. Tell you about his breakthrough idea, how it was vindicated, and what its impact has been in our understanding of the universe. The man was George Gamow. He was born in Russia 102 years ago. And as a young man, he showed so much promise in physics that he was allowed to work in Great Britain during the early 1930s. This is a picture taken of him at that time. He was ordered back to Russia during the early terrible Stalin years, but he was able to escape with the help of some famous scientists. Marie Curie was one of them, and he spent the rest of his life in the U.S. He had bright red hair and a very bright mind to go along with it, and he was good with sound bites. Here is one of them. The elements were cooked in less time than it takes to boil an egg. We'll learn why he said this. He wrote bad limericks and good popular science books, the Mr. Tompkins books that explained science in layman's terms. I remember reading his Mr. Tompkins Learns the Facts of Life when I was about 12 years old or so. I think I learned something about genes when I was hoping for something more anatomical. But at any rate, they're very charming books, and they're still in print after 50 years. Unlike cosmologists of the 1930s and 40s, who were essentially mathematicians and thought of the universe in abstract terms as solutions of equations, Gamow had an entirely different perspective. He viewed the universe as a huge nuclear physics laboratory, and in 1946 he became interested in how the chemical elements came into being. Well, I was in high school at that time and was learning about the periodic table, but I don't remember anyone discussing where the elements came from. They were just there. But this is the sort of outside-the-box thinking that Gamow enjoyed. At the time, astronomers had known for about 20 years that the distribution of elements in stars and in interstellar space was very different than it is on the Earth. On the Earth, carbon, nitrogen, and oxygen are plentiful, as are silicon, say, and iron in rocks. But that's not so at all in space. Each tick on the scale of this graph is a factor of 100 smaller than the one above it. This means that in the universe as a whole, all of the common terrestrial elements are rare, none of them making up as much as 1/100th of 1% of the total. But helium, which is rare on Earth, makes up about 25% of the total mass of the elements. The take-home message of this graph is that just the two lightest elements, hydrogen and helium, make up 99% of the familiar elemental matter in the universe. Well, where does all this stuff come from? We know now that except for hydrogen and helium, they are made in stars. But in 1946, no one knew that, and few people had even bothered to think about it. But Gamow had an idea. It had also been known for about 20 years that distant galaxies were all receding from one another. So maybe, Gamow reasoned, sometime in the distant past, all the material in the galaxies was concentrated in the form of a dense hot soup that he called Ylem, Y-L-E-M. Gamow found this word in an old English dictionary, and he liked the sound of the word. It means, roughly, stuff to make soup from. Gamow's soup, as he imagined it, had four principal components. It contained protons, neutrons, and electrons. The elements could all be made by putting together enough protons and neutrons, and then neutralizing the proton charges with the same number of electrons. To make the elements, this soup would have to have been cooked using thermal radiation. And Gamow set out to find the recipe. How long was it cooked and at what temperature? For starters, he asked himself, under what conditions would 2 protons and 2 neutrons come together to form a helium atom? We saw that that's 99% of the job. Since the probability of 4 particles coming together at the same time is very small, the process would have to have proceeded in steps. Step 1 would involve a single proton and a single neutron coming together to make the nucleus of a heavy hydrogen atom, which is called deuterium. But deuterium is a rather fragile nucleus, and the reaction can go backwards as well as forwards. So deuterium can be broken up by high-energy radiation, gamma rays, which, as we'll see, are abundant at high enough temperatures. So the temperature would have to be lower than about 1 billion degrees. Otherwise, deuterium will be broken up as fast as it's formed. The next steps involve, in one way or another, adding a proton to a nucleus with a proton already in it. Like charged particles repel one another, so getting 2 of them close enough together requires a lot of energy and thus rather high temperatures, at least 10 million degrees. So there is a window of temperatures between 10 million and 1 billion degrees where this series of reactions might work. The notion then was that the other steps are just repeats of the one above, adding neutrons and protons one by one to make all the heavier elements. Notice that I wrote thermal radiation as one of the components of the primordial soup. At this stage, the universe is a pretty simple place to understand. Simpler, in fact, than it will ever be again. But it's unusual because it's dominated by thermal radiation. And in a real sense, thermal radiation is what the universe at this time is all about. So we have to talk about thermal radiation some more. Well, it's a fact of nature that everything that is warm glows. The surface of the sun or a filament of an incandescent bulb are at about 5,000 degrees centigrade, and they emit visible light. The embers of a campfire, which is cooler than the sun, emits both light and heat in the form of infrared light. The surface of the Earth, cooler still, emits light at even longer infrared wavelengths. We don't see it, we feel it. Some of this radiation gets trapped by the CO2 in the atmosphere, the much discussed greenhouse effect, which is vital to regulating the temperature and the climate of the Earth. In the glow from a furnace, there is light of many wavelengths present. Radiation is continuously both radiated and absorbed from the walls in like amounts. We say that the radiation is in equilibrium with the furnace walls. And we can assign a temperature to the radiation that's the same as the temperatures of the wall of the furnace. When this happens, the distribution of wavelengths in the light present has a very specific shape, which is shown here in the middle figure, called a Planck distribution, named after the famous physicist Max Planck, who first figured out this shape. The important thing to remember is that as the temperature changes, the shape of this curve stays the same for all temperatures. It just spreads out or squeezes together. And the area under the curve, which represents the total energy at all wavelengths, is proportional to the 4th power of the temperature. The constant of proportionality, which I called A here, is the Stefan-Boltzmann constant. The only subtlety is that temperature must be in absolute units, absolute temperature. To convert centigrade to absolute Kelvin scale, you just add 273. So, for example, the Earth's surface is about 30 degrees centigrade, or about 300 degrees Kelvin. The next point is that light also has mass. Light weighs something. Why is that? Well, Einstein taught us that E equals mc squared. That's the most famous equation in all of physics. So since thermal radiation has energy, it also has mass, in exactly the same way that a bucket of water or a lead brick does. We know that because light is attracted by gravity to other massive objects. That, in fact, was the first successful test of Einstein's theory of gravitation. But unlike conventional matter, thermal radiation has a mass density, that is, a mass per unit volume, that changes with the temperature. In fact, the temperature completely determines the density of the radiation. Increase the temperature of the radiation by a factor of 10, and the mass density increases by a factor of 10,000. That's a big effect, and it will be important. So much for thermal radiation. Now let's get back to Gamow's fireball. So here are the conditions that Gamow finally settled on. The first deuterium step begins once the temperature falls below 1 billion degrees. But it goes faster and faster as the temperature continues to drop, and it will quickly, unless something's done, convert all of the protons and neutrons into deuterium. But this is a problem because there is still today a lot of hydrogen in the universe, as we saw, and there's very little deuterium. So something's wrong. Well, Gamow found that he had to fix this problem with some fine-tuning of the recipe. He found he could carefully adjust the initial concentration of neutrons and protons so that as the universe expands, collisions become less frequent. And the conversion stops, not because the temperature is too low, but because the soup has simply become too thin. The final composition that Gamow came up with was unlike anything that anyone had considered before. To try to get across how strange it was, let's compare it with the hottest material that physicists had had to deal with at that time, the center of a star. The center of the sun, or most stars, is at a temperature of about 10 million degrees, but the primordial fireball was at a temperature of 1 billion degrees, 100 times hotter still. The fireball is 20 times less dense than the center of the sun. In fact, it's about the same density as iron. So at this time, the fireball is hotter than the sun, but less dense. But the real shocker is that almost none of the mass, the weight, if you will, of the fireball is contributed by conventional matter. Even in something as bright as the sun, the mass of light is completely negligible. But in the fireball at this time, it's a state of matter in which radiation is so intense that it alone gives it the density of iron. In fact, we'll be getting to that, we now know that the mass of the universe was predominantly made up of radiation, a kind of light soup, for its first 50,000 years. Well, now let's switch gears. So far we've talked about the temperature and the density of the fireball, but not about when it would have existed. To bring in the element of time, we need some results from Einstein's general theory of relativity. Einstein found that in order to make gravity compatible with the rest of physics, it was necessary to consider space and time together as a single entity, which we now call spacetime. And he found that spacetime becomes curved in the vicinity of matter, and that this curvature of spacetime acts back upon the matter, telling it how to move. That's what we call gravity. That's an accurate but very general summary of Einstein's greatest achievement. As applied specifically to the universe, he found that in the presence of uniform matter, like our fireball, space can't just sit around doing nothing. It's not just a stage, it's an actor. It must either expand or contract, a fact that was initially an unpleasant surprise to Einstein. Even the greatest physicist of the 20th century had a preconceived view of the universe. He thought it ought to be static, and he tried, unsuccessfully, to doctor his theory up to make this possible. He later said that this was the biggest blunder he ever made. So Einstein's theory of gravity provides a conceptual underpinning of the expansion of the universe. It says that the expansion rate is controlled by the mass density. And this is why we were so concerned in what went before this about the mass density. But remember that Mr. Stefan told us that in a hot universe, the mass density depends only upon the temperature. So putting Einstein and Stefan together, we can work out the temperature of the universe as a function of time. Or, turning that around, we can deduce the age of the universe from its temperature. Here's the formula that gives the age of the universe if you know its temperature. I've taken the trouble to write it down, not just to intimidate you, but to point out something that's quite amazing. The constant of proportionality between the age of the universe and its temperature, all this complicated stuff here, just boils down to a single number, which you can calculate from other numbers, like the Stefan's constant, the velocity of light, and so forth, all numbers that had already been determined by experiments in a laboratory. No wild extrapolations are needed to find the temperature of the universe 13 billion years ago. It just required already well-known physics. I think Gamow was the first person to really appreciate this amazing fact. Well, when Gamow put in the numbers, he discovered that when the temperature was 1 billion degrees, the universe would have been only about 4 minutes old. And he predicted that the helium was made in just 6 minutes, about the time to cook a hard-boiled egg. Well, if Gamow was right about the hot fireball, what happened to it with the passage of time? To understand this, we need to follow a small volume of fireball material about the size of a sugar cube, say 1 centimeter on a side. The length unit chosen is irrelevant to the argument. When space expands, the volume grows to a cube that is larger, say A centimeters on a side, where A could be a big number. The relative increase in the volume when the side changes by A is A to the third power. On the other hand, the total amount of matter doesn't change. It has no place to go. So the matter density is diluted by this same factor, 1 over A cubed. Well, Gamow knew roughly what the present matter density is, and since he had chosen a corresponding value for the density of his 1 billion degree fireball, he could work backwards and estimate the expansion factor, A, that was necessary to make this consistent. He found that A should be about 200 million. Well, this number, 200 million, is a very important number because all other interesting quantities scale simply as powers of A. As space expands, the wavelength of light is stretched by this same amount, 200 million. And there's a definite relation between the temperature of light in thermal equilibrium and its wavelength, which says that if all the wavelengths increase by A, the temperature drops by this same factor, 1 over A. As we said, the density of matter is diluted by 1 over a to the third power, 1 over a cubed, but the radiation energy density falls faster as 1 over a to the fourth power. That's because, unlike conventional matter, light gets less energetic and thus less massive as it expands because it's stretched. This extra factor of a is why the mass of the universe is no longer predominantly in radiation. Well, there's a lot of information here to absorb, but the most important conclusion is the answer to the question, what happened to the fireball? The answer is that it expanded and it cooled. But the radiation should still be around. It's just that its temperature should now have cooled to about 5 degrees Kelvin. Being immersed in a 1 billion degree fireball would be very hard to miss. But sitting on a 300-degree Earth, could we know if we're also immersed in a 5-degree fireball? That is the remaining question. Well, Gamow and his young co-worker, a thesis student named Ralph Alpher, published these findings in a highly respectable scientific journal in 1948. The other name on the paper was a well-known physicist and a friend of Gamow, Hans Bethe. Bethe never worked on this paper at all. Gamow just added his name to make a pun on the first 3 letters of the Greek alphabet, alpha, beta, gamma. Mr. Alpher, fighting for recognition, understandably didn't think that it was very funny. And interestingly, the paper, even though it was amusingly co-authored by 2 heavyweights in the physics community, was largely ignored or forgotten. How come? Well, the stated aim of the paper was to show that all of the elements were made in the fireball, even though only the first step up to helium was worked out. This larger claim was simply wrong. No stable mass 5 nucleus exists to provide the necessary next rung in the ladder after helium. This was a problem that was already suspected by some experts in the field, including, quite possibly, the phantom co-author, Mr. Bethe. So many nuclear physicists simply discounted the entire paper. What about astronomers? Here there was a breakdown in communications. Gamow and Alpher were physicists, not astronomers. They later claimed that at the time, radio astronomers that they contacted told them that a 5-degree fireball remnant would be very difficult to detect. But for whatever reason, they didn't in this paper even suggest that such a search be made. Consequently, radio astronomers who were busy with other things weren't really made aware of the importance of devising experiments to search for the background radiation. Gamow himself began working on something completely different, deciphering the genetic code of the DNA molecule, whose structure Crick and Watson had just worked out. Gamow developed ingenious mathematical codes using the 4 nucleic acids as code letters. Even Crick became quite interested in his idea, but ultimately it made no sense biochemically and led nowhere. But still it diverted Gamow's attention at a critical time. There were also philosophical prejudices at work. Physicists have an annoying reputation for believing they can understand anything worth understanding. But even many physicists thought that trying to explain the entire universe was a classic example of scientific overreach. Also, it seemed all too simple. Even the physics of everyday things can be terribly complicated. Stirring a cup of coffee involves turbulent flow, which taxes the capabilities of the world's most advanced supercomputers to this day. By comparison, the calculations that Gamow made were simple. Back of the envelope, simple. Multiply a few numbers together and predict that the early universe had to be 100 times hotter than a star in order to produce helium. Another simple multiplication tells you that this would have happened when the universe was only 4 minutes old. Wasn't this all just too simple to be believed? Many scientists thought so. The upshot was that the now famous alpha beta gamma paper vanished almost without a trace. It took 14 years for the idea to resurface. In the process of testing the performance of their hand-me-down horn antenna, 2 Bell Laboratory scientists, Arno Penzias and Robert Wilson, shown here, accidentally discovered Gamow's fireball. As a result, cosmology was instantly transformed from a kind of mathematical pseudoscience into a mainstream branch of physics that had a verifiable Big Bang history to hold everything together. Once the remnant fireball was discovered, there was an intense activity to measure and understand it. The detailed calculations involved computer codes that tracked dozens of particle reactions that might have influenced the outcome. In particular, to be correct, the revised recipe had to include one more key ingredient, the very elusive particles called neutrinos. These detailed calculations, when they were carried out, showed that not only helium, but small amounts of deuterium and the light isotope of helium, helium-3, should have survived to the present. Moreover, the amounts of these trace isotopes depended critically on the initial concentration of matter that was assumed to be present, just as Gamow had foreseen. When these trace isotopes were measured experimentally, it was found that there was a narrow range of matter density shown by the narrow vertical bar on the graph that made everything work out right. So this gave, first of all, an increased confidence in the whole idea, and secondly, an improved, more accurate value of this primordial matter density. And this primordial matter density could in turn be used to accurately calculate the average present amount of matter in the universe. That is to say, the change of temperature pins down the expansion parameter, and together they pin down the present matter density, which works out to be about 1 atom in 40 cubic meters, which is about the volume of an office cubicle. On Earth, an office cubicle contains about 1 million billion air molecules, but in the universe as a whole, on average, it contains only 1 atom. This is not surprising. The universe, as we saw, started out as a very dilute soup of matter, and on average it only became more dilute. It's only the influence of gravity that has concentrated matter in certain parts of the universe into galaxies and stars and planets that makes life possible in a few special places in an otherwise very empty universe. Well, this is more or less the history that I wanted to cover, but now I want to spend just a few more minutes in understanding in more detail what was accomplished. In discussing thermal radiation, I talked about an oven cavity filled with radiation. I want to describe in more detail what our cosmic oven consists of. All of the universe that we can ever know is contained in a sphere with a radius of about 13 billion light years. When we look out in space, we look back in time to a younger, hotter universe. So we are immersed indeed in a cosmic oven with the Milky Way at its center. At the outer edge of the oven are events that occurred 13 billion years ago. Helium was made in the first few minutes, very close to that outer edge. At first, the radiation in the fireball was being constantly scattered by collisions with a dense fog of electrons. But after a relatively short time, about 300,000 years, the temperature had dropped to about 3,000 degrees Kelvin. Then the fireball was cool enough that the electrons that scattered the light combined with the protons and the helium nuclei to make neutral atoms, and suddenly the fog has lifted and light is able to propagate freely. Since that time, light has just streamed toward us and reaches us today. Technically, the radiation was last in equilibrium 13 billion years ago, when the light left the oven walls, but the expansion of space itself has preserved the shape of the wavelength distribution while increasing the wavelength by another factor of about 1,000. In seeing this cosmic microwave background, we are seeing as far back into the early universe as we can ever hope to see. Anything that happened before that time, including the production of helium itself, was shrouded in this outer skin of electron fog that light can't penetrate. Gamow was told that the cosmic microwave background would be very hard to measure. Is it very, very weak? Well, yes and no. There was a lot of radiation in the early universe, and remarkably, although it has been much diluted, essentially all of it is still around. Each cubic centimeter of space contains nearly 400 photons of cosmic background radiation. These photons are continuously bombarding the Earth today. On the other hand, the radiant energy flux at the surface of the Earth is only about 2/billionths of that coming from the Sun. So there are a lot of photons, but because their wavelength is stretched, they no longer carry much energy. This, of course, is a good thing. It prevents living beings from being instantly fried by the remnants of the fireball. But if this radiant energy is so weak, you must really need sophisticated equipment to detect it, right? Well, no. Yesterday, that is, in the past 20 years ago, nearly every household in the world had one or more devices capable of detecting it. About 1% of the snow that you saw on your old rabbit ear antenna TV screen on an inactive channel was due to this cosmic microwave background. The noise temperature of a TV antenna is at about 300 degrees Kelvin, and noise is proportional to temperature, so about 1% of it is due to this microwave background. Here's another question. Can we really assign an accurate temperature to this radiation? Well, there have been several precise measurements of the wavelength distribution of the cosmic radiation using satellites and balloons. It turns out that the shape is just that predicted by Planck. The error bars have to be magnified 20 times in this figure just to be visible. John Mather and George Gamow, two physicists who perfected the techniques for these measurements, were awarded the 2006 Nobel Prize in Physics for their work. This was the second Nobel Prize for cosmic radiation. Penzias and Wilson got one in 1978 for its discovery. And Max Planck got the Nobel Prize in this area in 1918 for figuring out the shape of the curve. When all these measurements were first announced at a scientific conference, I'm told that a gasp of surprise went up from the audience. Why the surprise? Well, this means that the notion of an equilibrium fireball was not just some rough approximation to the truth. It means that cosmic radiation can really propagate for 13 billion years and still precisely remember its last scattering surface. And why is this a big deal? Well, one nagging question in cosmology is this. How do we know that the laws of physics don't change over time? This curve is proof that what Stefan and Planck found out about thermal radiation in the year 1900 in a laboratory in Berlin was also true 13 billion years earlier in all of the most remote places of the universe that we can ever hope to see. So let's summarize. George Gamow and his collaborators, Ralph Alpher and another man named Frank Herman, who were less flamboyant and more easily overlooked, which is a shame, all three deserve tremendous credit for pursuing the idea of an early hot universe to its logical conclusion. Using the known thermal properties of light, they showed that the early universe must have been so hot that its mass consisted mostly of radiation. This radiation, cooled by cosmic expansion, is still reaching us today. They were able to show that essentially all of the two most common elements, hydrogen and helium, could be formed in this hot fireball. But they were unable to find a way to make all the elements in this way. So the work was forgotten until the accidental discovery of the remnants of the hot fireball. This transformed the study of cosmology from something considered to be a pseudoscience into the active and the extremely productive field that it is today. It would take another talk to go into all the new insights that have resulted, but let me mention just one. Although we now know that the rest of the chemical elements were produced within the interior of early generation stars, we are also virtually certain that the chemical elements familiar to our world make up only about 4% of the present mass of the universe. The rest can't be radiation, which has now been redshifted to the point where it has insignificant amount of energy content. The nature of the remaining 96% of the mass is quite simply unknown. There's no shortage of exotic ideas, but they're all conjecture at this point. We just don't know. Let's end with a graphic summary of the history of the universe. It shows the radius of the visible universe plotted against time. We've talked only about a small but important sliver of time in the history of the universe, which is shown by the pair of white horizontal lines. At these and later times, we think we have a firm grasp of the physics. It's true that we can't account for a major fraction of the mass of the universe, but that's presumably because this stuff, whatever it is, was produced at still earlier times at energies that were too high to have been studied yet here on Earth. This represents the area above the knee in the curve, which is terra incognita, that is, unknown territory. There are plenty of ingenious suggestions for what went on even here, but it's conjectural and there's plenty of room for fresh surprises. Finally, I want to mention that there are a couple of good books that cover the history of modern cosmology. Simon Singh's book made the bestseller list for a few years ago, and Steven Weinberg, who is a Nobel Prize winning physicist and cosmologist, has written a very masterful popular account at a slightly more technical level. So if you want to continue to learn more about this, those would be two good places to start. Well, thank you very much for listening, and I'd be happy to try to answer any questions that you may have.